Okay, so I guess we can start. So in the last two lectures, we did an overview about cosmic ray propagation and the acceleration of cosmic rays from supernova remnants and the pulsar wind nebulae. I just wanted to give you just an example of why it's so important to study first astrophysics before studying dark matter. The reason is that if you want to study dark matter in cosmic particles, for sure dark matter will be very likely a subdominant contribution of the cosmic ray flux. So you really have to know precisely the astroparticle and astrophysical production of cosmic rays before trying to find any signal of dark matter. This is an example of the antiproton flux measured by AMS, and the secondary production due to the cosmic ray collision with interstellar medium atoms is given by this band. And there is a small excess here that could be due to dark matter, but if we have an uncertainty for the astrophysical production of antiprotons that is larger with respect to this excess, there is no way we can really claim that this is a detection of dark matter. Okay, so we spent the last two lectures talking about astrophysics because astrophysics is incredibly important to increase the discovery potential of dark matter with cosmic particles. Okay. Now, in the lecture of today, we are going to talk about dark matter. We will do a overview about dark matter, talking about gravitational evidences, some general properties about the mass of dark matter. Then we will focus on weakly interacting massive particle. We will show two mechanisms that can explain the current abundance of dark matter. And then we will talk about dark matter density and velocity distribution. And tomorrow and the last day, instead, we will show some of the most studied strategies to search for dark matter in cosmic rays and gamma rays. Okay, so let's start with something about the evidences of dark matter. So far, we have only gravitational evidences, so no dark matter particle interaction has been ever detected in laboratories, even if there was a huge effort on the experimental point of view to try to detect dark matter interactions. But instead, the gravitational evidences are really overwhelming. So typically, in order to study the density of dark matter, we use a quantity that is the omega dark matter, and this is the density divided by the critical density of the universe. So in general, you can study the different components of the universe. This is with this omega factor, that is the ratio between the density of that component divided by the critical density. And so in particular for dark matter, there is another way to describe the density, multiplying this for h lowercase squared, where h lowercase is the Hubble constant divided by 100. So this is roughly equal to 0.67. And so h squared is roughly 1/2. And the omega dark matter h squared is measured very, very precisely with the anisotropy of the cosmic microwave background, with an error that is at the basically at the per mil level. This one is today, yes. Yeah, in general, you can write, yeah, this is today, so you should put yes. But of course, age in general can depend on the temperature and the age of the universe, yes. And dark matter makes most of the matter in the universe. In fact, the value for the baryonic matter is equal to 0.02237. Also, this one, of course, is measured very, very precisely. So roughly speaking, if we just calculate omega, this makes basically 26% is made of dark matter, while instead roughly 4.9% is ordinary matter, okay, baryonic, let's say. So dark matter makes roughly 85% of the total matter in the universe. So gravitationally, you might expect that dark matter really dominates the gravitational potential in galaxies and in galaxy clusters. So we have evidences for gravitational effect of dark matter from different objects, from single galaxies up to galaxy clusters, and also considering cosmological observations. Probably one of the easiest evidence that we can have and we can explain are the rotational velocities. So the idea is that you can observe galaxies. They have a galactic bulge. They have a disk. In the disk, you have spiral arms, and in the spiral arms, you have most of the stars. The star rotates around the center of the galaxy, and using the Doppler effect, you can measure the rotational velocities of stars. The galaxy, if we take the Milky Way, this is roughly with a radius of 15 kiloparsec. Most of the gas and stars are located within 15 kiloparsec from the center. And so we can measure just with Newton's law of gravity what is the expected trend of rotational velocity with radius. So we make the centripetal force equal to the gravitational force. And we put R here because the star can be located at a specific point. And if this R is within the radius of the Milky Way of the galaxy, we have to evaluate the mass up to that radius. But if we make R lowercase larger than the radius, we can substitute here m as a function of R with the total mass of the galaxy. And so we can write that the circular or rotational velocity is expected to be g mass of the galaxy divided by the radius. Okay, so you expect to have a decreasing trend with the square root of the radius. And but very surprisingly, as we see here in these figures, this is a collection of different rotational velocity data. For radii larger than roughly 10 kiloparsec, all this data points towards a flat rotational velocity. So only considering the gas and the stars, this is not sufficient to explain this data. So typically you see that the bulge is peaked at a fraction of basically 1 kiloparsec, then it goes down because the density of star decreases as a function of radius. Instead, the gas component is more or less flat, but there is an overall normalization that is much smaller with respect to the data. Yeah. The mass of the gas? With emission lines. So basically you observe emission lines at different directions. According to the element that is emitting the line, you can reconstruct what element it is. And you can reconstruct the ionized, the neutral, molecular. We do exactly the same in our galaxy. And with this, we have the interstellar emission in gamma rays, for example. Instead, for the stars, we can, for example, measure the Doppler effect, or we measure the relation between the luminosity and the mass. But as you can see, basically, if you sum, okay, here is a bit small, but this is the bulge, this is the gas. If you sum these two, there is no way to get this number that is a factor of 4 larger with respect to the other contributions. So you really need to add something else. What you want to add is something that should give a velocity that is constant. So in order to do this, we can basically see that the mass should be proportional to the radius. The mass is equal to 4 pi integral dr r squared rho, the density. So if the mass should be proportional to r, this means that the density should be inverse proportional to r squared. Okay? So if you consider a radius larger than, let's say, 10 kiloparsec, you can explain these observations by considering a spherical halo of dark matter with a profile 1 over r squared, and the size of the halo should be at least tens of kiloparsec, because this data reach even 100 kiloparsec. So you expect that this sphere of dark matter should be at least, let's say, 100 kiloparsec. Okay, then another very interesting evidence comes from gravitational lensing. You probably know very well this effect. The effect is due to if you have a very massive object like a galaxy cluster, but you have also a galaxy behind the galaxy cluster. So this is the galaxy, this is a galaxy cluster. You can see the image of the galaxy as a ring, Einstein ring, of a portion of a ring, of a small arc, when you see this object. And this is due to the fact that light curves around the very massive galaxy cluster. And so basically the curvature of the light is expected to be proportional. So this is the angle of curvature. And this is expected to be 4 times the gravitational constant, the mass of the object divided by basically the distance, the impact factor of the observation. But the important thing is that the curvature is expected to be proportional to the mass. So if you assume that the mass of the galaxy cluster is just baryonic, you don't see the curvature that we observe in several images. Okay, so for galaxy cluster, it's clear that for gravitational lensing, it's clear that baryonic matter is not sufficient. Another very interesting evidence with galaxy clusters is related to the so-called bullet cluster. This is probably one of the most famous examples of dark matter evidence. This is the result of the collision of 2 galaxy clusters that happened basically 150 million years ago. So before the collision, the 2 galaxy clusters were 2 separated objects, where you have the gravitational, let's say, the gravitational potential made as a sphere. In the center, you have the galaxies. And basically in between between the galaxies, you have the gas that is observed, for example, in X-rays. Then these 2 galaxy clusters collided, and basically the galaxies are basically collisionless, because they are so small compared to the size of the cluster that they don't scatter each other. The gas instead can basically interact efficiently with the other atoms of the other gas, and so they slow down. And so here, this image is basically, this represents the green contours are the gravitational lensing maps. So this is basically, this is tracing the mass of the total mass, the dark matter component. Here in this same place, you also have the galaxies, but instead the gas is basically remained in the center, because the gas collide, it slowed down, and it remained displaced with respect to the position of the galaxies and the dark matter potential. So using this observation, we can estimate the self-interaction of dark matter. In particular, the fact that the dark matter is placed around the galaxies, this means that the probability, we can write a probability for the self-interaction of dark matter. This probability is given by the self-interacting cross-section, the density of dark matter, and the radius of the cluster. And this probability should be smaller than 1. Because if you had a large probability, you would have not seen the dark matter, basically the gravitational lensing located around the galaxies. Now we can rewrite this as a function of the cross-section. Basically, the density of dark matter is the mass multiplied, the mass of dark matter multiplied for the number density. And so we can rewrite this probability as a function of mass and density, and we can find an upper limit for the ratio between the self-interacting dark matter cross-section and the mass that should be smaller than 1.8 millibarn over GV, or roughly 5,000 over GV squared. Now, do you remember what was the number we wrote yesterday for strong interactions? This was roughly 40, 50, right? Millibarn. So this means that for the observation of the Ballet cluster, we see that the self-interaction of dark matter, the cross-sections should be much, much smaller than the one of strong interactions, okay? So we know that dark matter should be weakly interacting among themselves and also with ordinary matter, okay? There is also another way to estimate this number using the drag force, and if you are interested, you can see the calculations in the notes. Yeah. Because it takes time. If you have two, so the dynamic of two galaxies interacting, first they go through each other, then there is, it takes time for the system to virialize into a unique object, okay? So maybe after, I don't know, after a lot of time, you will see the two. Because the gas feels the cross section, okay? So they slow down and they are centered in the center. Dark matter just feels gravity, but gravity takes time to merge and to virialize in a unique object, okay? Okay, then cluster of galaxies actually probably were one of the first evidence of dark matter thanks to the study of Zwicky of the coma cluster. In particular, what he did was to observe the coma cluster. He measured the luminosity of the coma cluster. The luminosity gives a value of the luminous mass, so the mass related to baryons. But the luminosity mass is not the real total mass of the cluster of galaxies, because you have also the gravitational mass that, as we saw, is actually much, much larger. So in order to estimate the real gravitational mass of a cluster of galaxies, you can use the virial theorem. So the virial theorem basically relates, so if you have a system of objects that are in equilibrium, you can relate the average kinetic energy plus the average gravitational potential using this relation here, okay? And using this relation, you can so find that the basically you expect that the gravitational potential of in order to explain the gravitational potential in the coma cluster, you really need that dark matter makes basically 85% of the total matter. The baryonic mass is just 1-2%, oh sorry, the stellar part is just 1-2%, and the gas component it's basically between 14%. Okay. And actually, we have a lot of observations of cluster of galaxies also after Zwicky, and this is something that is always confirmed looking to different objects. Okay, then there is another quite different observation that actually gives the precise estimate about the dark matter density. This is related to the anisotropy of the cosmic microwave background. So the CMB is the result basically of the universe becoming transparent for light. So in the early universe, when you started to have atoms, the universe was still too hot to keep atoms. So light was efficiently colliding against atoms and it was extracting the electrons. But then the universe cooled down and the universe was too large and too cold for photons to still extract electrons from the atoms. At that time, that is roughly 380,000 years after the Big Bang, light was free to move in the universe. And so if you make a measurement of the anisotropy and the distribution of the temperature of the CMB, you basically have a snapshot of the dark matter distribution of the universe at that time. The CMB map is basically isotropic, except for small temperature fluctuations of the order of 10 to the minus 5. And if you measure the anisotropy and the power spectrum of the CMB, you have a precise measurement of all the components that at that time were important for the universe evolution. So you have an estimate of baryonic mass, dark matter, baryonic density, dark matter density, dark energy density, and radiation. And in particular, you see here how the power spectrum of the CMB changes with less or more dark matter. Okay. So since the CMB data are extremely precise, even by varying little amount dark matter density, you can basically mess up your prediction with respect to the data. And so the CMB data are providing really, really precise estimates for the density of the different components of the matter and energy. Yeah. Basically, so there are some peaks. So there are some peaks that increase, and also you have a change in multiple. Baryonic mass, dark energy, dark matter changes in different ways the power spectrum of the CMB. In fact, you see that, for example, this peak can go down, this one is moved towards the right, so it's not that obvious how the different components can change the CMB power spectrum. And also it's important that in order to fit the CMB, you really need a complete model, that is a lambda CDM model. So you need dark energy, dark matter, baryonic, and radiation. Okay. Okay, very good. Okay, so now we can try to interpret all these observations. And there are at least two ways that you can pursue to interpret these observations. One is with modified gravity, that is not the focus of these lectures. And the other possibility is that the standard model cannot explain these observations. You really need something new, at least one new particle. This is something important, is at least one new particle, okay? It's not only one. It can be that you have a completely new BSM beyond the standard model theory, and this BSM model has more particles, and among these particles you have maybe one that is the lightest one that can be a the dark matter candidate. So in order to interpret all the observations we talked about, if dark matter is a new particle, this dark matter particle should behave as matter. Okay, so it means that basically the density should be proportional to 1 over volume. Okay, so the equation of state should be omega equal to 0. The second point is that it should be what is typically called as cold, so non-relativistic in the matter radiation equality. So when you start to have the structure formation, it's very important that it's cold because we know that structure in the early universe started to form from the small overdensities, and then these small overdensities increased in size until at redshift equal to 0. So nowadays you have a galaxy and cluster of galaxies. If dark matter is not cold but is hot, instead it's not possible to have this structure, so this bottom top scenario, but you would have the top bottom, so from very large structures, so super cluster of galaxies, these decompose into smaller galaxies and cluster of galaxies. But we know that this is not how structure formed in the universe. And so dark matter, or the dominant component of dark matter, should be cold. Then it should be not interacting, or at least weak interacting. And we saw the upper limit. So basically we expect that the cross-section is of the order of the weak interactions. Now, the fact that it's not interacting does not mean that it's impossible to have dark matter particles interacting. Otherwise, there is no way that we study dark matter production of cosmic particles, okay? So it's weakly interacting, and we have to study with cosmic particles at what level this interaction is weak. Then it should be non-baryonic, and it should not emit light. The charge is expected to be 0 or extremely small, and be relatively stable, or at least with a decay time much larger than the age of the universe. Is the ratio between the density and the... Mhm. Okay. But that is the dark matter or is the inflaton? I have to think about it, yeah, at the moment. Yeah. Ah, okay. Mhm. Thanks, Nicola. Okay, so these are the, yeah, basically these are the main characteristics of dark matter if it is a new particle. There are a lot of possible candidates, really, with masses from fuzzy dark matter 10 to the minus 20 electron volt up to almost to the Planck scale. Now I would like to show you some very simple calculations that can actually make a range of possible masses, just using basically quantum mechanics. So let's first talk about scalar dark matter. Okay, in scalar dark matter, you don't have any problem about the Pauli exclusion principle. So we can use simply the Heisenberg uncertainty principle. So then you can write that, so the delta, basically the uncertainty in the momentum is roughly equal to h divided by the size that is bounding dark matter. Delta p, so is equal to mv, that is equal to h divided by the size. And so we can find that the velocity should be equal to the Planck constant mr, okay? So what you can see is that if m becomes very, very small, you have that the velocity becomes very, very large. So this is a sort of quantum pressure that if it is too large, basically makes impossible to structure to start to form because the velocity of dark matter is too large. And if you apply this to dwarf, you find that the mass of dark matter as a scalar should be larger than 10 to the minus 22 electron volt. Typically, when we talk about such small masses, we refer to fuzzy dark matter. Okay, so fuzzy dark matter cannot go lower than this value for mass. Otherwise, it's impossible to form structures in the universe because the quantum pressure is too large. Yeah. You can also change that? Mm, I don't know. Yeah, I'm not sure. It's just this is just using the uncertainty principle and then looking to how dark matter is for basically the density of dark matter around dwarf. Then maybe you can tweak a bit the model and change the way dark matter is made and maybe evade these models. Yeah. In fact, when we study fuzzy dark matter, basically, typically the plots are for masses even below these limits, 10 to the minus 22, because probably you can change a few assumptions. And instead, if dark matter is fermionic, in this case, you have the Pauli exclusion principle, for which you cannot have two fermions in the same point of the phase space. And so we can write that the mass of the halo is equal to the mass of the dark matter multiplied for the volume and the integral of the phase space. Now, in natural unit, basically this must be at most 1. Okay, if we would not have used natural unit, this is basically equal to g, so the number of degrees of freedom divided by h. But in natural units, we can write it as 1. And so basically this gives roughly m fermion multiplied for r cube of your astrophysical object, mass fermion velocity cube. And if you apply this again to the dwarf, you find that the mass, basically the lower limit for the fermionic mass of dark matter is roughly 0.7 keV. So as expected, the lower limit for fermionic dark matter is much larger with respect to scalar dark matter. Okay, then in the standard model, actually, we have a particle that could have properties similar to, at least some of the properties similar to dark matter, that is a neutrino, right? Neutrino is weakly interacting. We know that it exists. We know that it was important in the early universe. But the problem is that there are two properties of the neutrino that basically don't match with the dark matter observations. The first one is that the relic density is too small. In fact, the relic density for neutrino is given by this equation, where this is the sum of the masses for the different families of neutrinos. And using basically from different experiments, we know that this number should be smaller than roughly 0.1 electron volt. And so if you plug in the number here, you find a relic density of neutrino that is basically 0.001. So this is absolutely too small, okay? So I just wanted to make very precise that, okay, there is a particle that could behave as dark matter and probably is a fraction of dark matter in the universe, but the density is expected to be much smaller than the dominant component of dark matter in the universe. Okay, so dark matter should basically be located around galaxy and galaxy clusters with a density that scales as 1 over r squared. And in order to study the evolution of dark matter, sometimes the sound is cut, right? Is it only my impression? No, it's continuous, okay. So in order to study the evolution of dark matter, we can use the phase space density of dark matter, that is a function of position and velocity. This is basically probability to have dark matter in a given position and the velocity. And this means that integrating in the entire volume and for the possible velocity, this should be equal to 1. And in particular, to study the evolution of dark matter, we can use the Boltzmann equation. So that basically dictates that the Liouville operator that represents how the dark matter phase space density evolves in the universe, this should be equal to the collision operator still running on F. If you take the non-relativistic case, the Liouville operator can be written as derivative of F over time, velocity, derivative of F over space, plus the acceleration, derivative of F over velocity. And then you have the collision operator. Now, just an academic exercise, let's assume that collisions, so dark matter annihilation or scattering against standard model particles, is not important, okay? So we just follow this isothermal sphere of dark matter evolving just with gravity, okay? So we make the collision operator is equal to 0. So this represents how the phase space evolves in the non-relativistic case just under gravity. The solution to this equation, basically you can find it using the Jeans theorem. And you can find that the solution can be found by assuming that the phase space can be written as a function of energy, where energy is basically the gravitational potential, and then you have the kinetic energy. And in particular, we can assume that the distribution of dark matter phase space in density follows the Maxwell-Boltzmann distribution. So it's basically an exponential of minus the energy multiplied for a constant beta that for the Maxwell-Boltzmann is basically the inverse of the temperature. But in this case, we keep it generic, okay? So we can write the phase space as a function of energy, and we take a Maxwell-Boltzmann distribution. Using this assumption, we can relate the density with the integral of velocity squared of the phase space. And by doing this integral, you find that this is equal to an exponential factor of minus the gravitational potential divided by sigma squared. So this is the proportionality of the density, but this depends on the gravitational potential. So it is still not as a function of either radius or velocity, so it's not very useful. In order to extract the dependency with the radius, we take the Poisson equation for the gravitational potential that is related to minus 4 pi g rho, and plugging in the dependency of rho with the potential, we can find that the density is in fact proportional to 1 over r squared, and the distribution of velocities is basically Gaussian function with dispersion sigma squared. Okay, so what we have done is that basically we have assumed no collisions matter particles. We have solved the Liouville operator on the phase space density, assuming some simple Maxwell-Boltzmann distribution for the phase space density with energy. And we found exactly what is expected from the rotation curve galaxy. So density is proportional to 1 over r squared, and the velocity distribution is basically a Gaussian function. And this is exactly what is expected for an isothermal gas sphere affected by just by gravity. Okay. But remember that here we have neglected the self-interaction of dark matter. Okay, maybe we can do, yeah, let's do just, now we have to study more in detail what happens when dark matter collide and annihilate. And in particular, we have to study how dark matter density evolved in the early universe. There are at least two frameworks that we can consider. The first one is that dark matter was in thermal equilibrium with the standard model particles. So we can consider after the Big Bang, the temperature was extremely high. Standard model particles were basically all relativistic. And you had dark matter particles annihilating and producing standard model particles, but also the opposite was basically had the same probability. And this means that dark matter was in thermal equilibrium with the early universe SAP of particles. And so this implies that all the particles in equilibrium are sharing the same temperature. Okay? This is the first assumption. Dark matter was in thermal equilibrium in the early universe. The other possibility is that dark matter has never been in thermal equilibrium with standard model particles. These, of course, are two very different cases, and we will show briefly how you can manage to have the right Rayleigh density in the two cases. So in case dark matter was in equilibrium with the early universe, you can write the energy, basically the density, as the integral in momentum of the phase space. G is the number of degrees of freedom. Rho, the density, is the similar, but you integrate also in energy. And the pressure, you integrate the momentum squared 3 times the energy. So we will focus mostly on the energy density. So we will follow the evolution of the energy, the density in temperature. And let's keep in mind that if the temperature is much larger than the mass, so we have a relativistic particle, the density is proportional to T cube. Okay, this is in particular written here. Okay, so the proportionality is T to the cube. And G, you keep the G, and this is for different cases, if it is fermionic, bosonic, or you take just Maxwell-Boltzmann distribution. So if in this case is equal to 0. And instead, the density is proportional to T to the 4th power. But if you have a particle that becomes non-relativistic, the density scales with, so T much smaller than M. The density becomes proportional to T to the 3 over 2, But the most important thing is that you have this exponential factor, okay? That works as a suppression, a very large suppression of the number density. And this will be very, very important when dark matter becomes non-relativistic, okay? What is the? Here is the mass of dark matter. Yeah. Okay. Another important thing is just let's briefly talk about the degrees of freedom. So when you talk about the total density, typically we take into account the density of relativistic particles. And you can sum the degrees of freedom for relativistic particles that are bosonic or fermionic. So you will see in the calculations G rho, this means the relativistic degrees of freedom, the degrees of freedom for relativistic particles that enter inside the density. Instead, when you see Gs, these are the ones that are present in the entropy calculation. Okay, so in the entropy S rho plus momentum divided by the temperature, you will see this Gs that simply is the same thing but with a different power of temperature. Okay, so when we talk about G rho or Gs, these are the total degrees of freedom of relativistic particles. And the G rho or Gs in the early universe was roughly 100. When the temperatures go down, particles start to be relativistic, and so the G numbers becomes of the order of 4. Okay. Okay, so I guess okay. Let's do also before making the break. Yeah, let's start the calculation of the freeze out. So if dark matter was in thermal equilibrium with the standard model particles, you had two interactions that are important. One is the annihilation, so dark matter annihilating into standard model particles. This is an inelastic process that keeps what is called the chemical equilibrium. You have another process that instead is an elastic process, dark matter, standard model, that instead keeps the kinetic equilibrium. So if dark matter is cold, you first have basically the coupling of these interactions, so you lose chemical equilibrium, but dark matter particles are still in thermal equilibrium thanks to the inelastic scattering. And after some time, you also leave the kinetic equilibrium, and so particles of dark matter are free to move in the universe. Okay? And when they are free to move in the universe, you start to have structure formations. And this is the area where it's important that dark matter is not relativistic. Because if they decouple from also the kinetic equilibrium and they are very, very fast, the velocity prevents structure to start to form. Okay? Okay, so let's start the calculation. We go back to the Liouville operator. And actually, we go back to the Boltzmann equation. So we write the Liouville operator on the phase space. This can be written in another way, just as a function of energy. Then you have the scale factor of the universe that is expanding. So this is basically the Hubble constant. Now we want to follow the evolution not of the space density, but we want to study the density n. And so we can apply this integral also to the Liouville operator. and this becomes 1 over a cube derivative over time of na cube. And this is equal to the first part of the Boltzmann equation that is typically used for the freeze out. Okay, so this is the part that takes into account just the evolution of the density due to the expanding universe. And let's do again the exercise that we did before. Okay, let's assume that you just have the Liouville operator and the collision operator is equal to 0. So this means that this is equal to 0. So what's the consequence of this being 0? What should be constant if this is 0? This part should be constant. And is this something expected? Yes, because this means that the density should scale as 1 over the scale factor cube. That is exactly what you expect with no collision. The density of dark matter just evolves with the expanding universe. So it should be inverse proportional to the volume of the universe. Okay. Unfortunately, or fortunately, I don't know, but the collision operator is not 0. So generally speaking, the collision operator takes into account a sum on the degrees of freedom of the particle, so the spin, an integral in the amplitude of the process. In particular, 1, 2, 3, 4 means, in this case, 1, 2 is the dark matter, 3, 4 are standard model particles. So there is the amplitude for the process dark matter annihilating into standard model, and you also have the opposite. F is the phase space of dark matter and standard model particles, and the plus minus are the Pauli blocking and Bose enhancement factors that takes into account plus for bosons and minus for fermions, because you have the Pauli exclusion principle for fermions, and this decreases the phase space for dark matter. And then you have the delta to conserve the 4-vector momentum, and you integrate over the total phase space. Do you think that we typically solve all this equation? Unfortunately, no. We have some assumptions that we can do to simplify significantly this equation. So the first assumption is that you have kinetic equilibrium, okay? So before the chemical equilibrium is lost, you keep the kinetic equilibrium, okay? So the annihilation, basically the scattering rate for this interaction is much larger than the one of inelastic. The second is that we can forget about Fermi and Bose statistics, and we can just assume Maxwell-Boltzmann distribution. And this is fine until the occupation number of dark matter is not that important. And we can so approximate these factors with 1. And then standard model particles are in thermal equilibrium with the photon bath, okay? So if we do basically this, if we follow these assumptions, the integral of the collision operator gives, so this is the part of the Liouville operator, and this becomes equal to minus the average of the annihilation cross-section. This is the thermal thermally average cross-section of dark matter particles, plus the sigma v for standard model particles, annihilating and producing dark matter particles, okay? Now, let's have a look to the signs, okay? So, here you have minus, here you have plus. Here you have minus because this is considering a depletion of dark matter, because this is dark matter annihilating, so the number of dark matter particles decreases. Here you have plus because here you have standard model particles annihilating and producing dark matter, and so you have an increase of the dark matter number. As I said, the standard model particles are in equilibrium, so we can write that the sigma v 1, 2 of dark matter particles are identical, so n1 and 2 we can write it as n equilibrium squared. The process of 1, 2 giving 3, 4 is the same of 3, 4 giving 1, 2. And so this is equal to sigma v 3, 4 and standard model particles. Okay? So basically the standard model particles are in equilibrium and they have the same rate of producing the opposite process, and so we can write this equation here. And so finally we find the Lee-Weinberg equation for the evolution of the density. That is this one. Okay, so this part is related to the expansion of the universe. This is the thermally average cross-section, this is the equilibrium density, and this is the dark matter density. See. Why we have plus minus here? No, sorry, this is what just I was saying. This one is because it's depletion, as this one is, yeah. No. But thanks for asking. Okay, now, there is a trick that we typically use to solve this Lee-Weinberg equation. And the trick is that we don't use the density, but we use a quantity y that has different names, so comoving number density. For example, one name is comoving number density. That is the density divided by the entropy. Why are we using this quantity? The reason is that the entropy, S, is proportional to T cube. And when you have dark matter that is relativistic, you still have T cube. Okay? So by using this comoving number density, when dark matter is relativistic, if you make a plot of the evolution of y as a function of x, that is the mass divided by temperature, at the beginning y is constant. It's convenient to follow the evolution as a function of y, because in this way at the beginning is constant. Okay? Then dark matter will become non-relativistic, and so y is expected to have the sorry. You expect to have the Boltzmann suppression, and so the equilibrium density is expected to fall. Okay. So if we write the Lee-Weinberg equation using y, and also with x, that is the mass over the temperature, this is dy over dx equal to minus entropy sigma v, Hubble constant as a function of x, and then you have y squared minus y equilibrium. Okay? Where the sigma v, thermally average cross-section, is a cross-section that follows the temperature evolution. So if you write this in a general way, this should be calculated as follows. But then, fortunately, there are simplified equations using Bessel functions. And in particular, typically, this sigma v is written as a function of expansion of velocity. So this is typically written as b0 plus b1 v squared plus additional term. So this term that does not depend on velocity is the S wave part of the cross section. This one instead is the P wave component. For indirect detection, if you have a P wave model of dark matter, typically the signal for indirect detection is very, very small. And the reason is that in astrophysical environments, in galaxy clusters, the velocity is expected to be, let's say, at most 10 to the minus 3, okay? So V squared creates 6 orders of magnitude of suppression. But this is nowadays in astrophysical environments. In the early universe, dark matter could be relativistic, so V is expected also to be of the order of almost 1, okay? So the suppression for P-wave dark matter is not that big as in the current universe. Okay, so now the two important quantities to evaluate the evolution of dark matter density is the annihilation rate that is equal to the density of dark matter multiplied for the thermally average cross section, and how this is compared to the Hubble rate. So if the annihilation rate is much larger than the Hubble rate, the process is very efficient and you keep having dark matter in equilibrium with the standard model particles. But when the annihilation rate starts to be much smaller than the Hubble rate, the annihilation processes are not efficient, and dark matter starts to decouple from standard model particles and from the thermal universe. And you have the decoupling of dark matter particles and the so-called freeze out. Okay? One of the key calculations, one of the key points of the calculation of the freeze out is to evaluate when the freeze out happens. Now, to be clear, there is not a specific time at which this happens. So there is not a universal, let's say, universal assumption that tells you at that temperature all the dark matter particles decoupled. But we can do a rough estimation that the freeze out happens when the annihilation rate is equal to the Hubble rate, okay? So we can write the annihilation rate as the dark matter density. The dark matter density when dark matter are non-relativistic. And this should be equal to the Hubble rate, or the Hubble constant. Well, you know, it's not a constant, the Hubble factor. Okay, so here we have that this equality is true when the temperature is the freeze out one. So this at freeze out, this is the freeze out, and also G is evaluated at the freeze out. Okay, so in order to find the freeze out temperature, we can solve this equation. I mean, it's not that easy. It's a numerical, you can find it with a numerical solver. And basically the solution for the standard WIMP dark matter is that the freeze out temperature is around 2030. We can typically take an average around 25. Now, keeping in mind that the XF is the mass divided by the freeze out temperature, this means that the freeze out temperature is roughly 20-30 times the dark matter mass. Okay? So this is basically the more or less the temperature of freeze out we are talking about. Sorry, yes. Yeah. temperature, mass, yeah, the mass, thanks, Pedro, divided by, let's say, 25, just to give a number, okay? Okay. So this will be the number for freeze out that we will use in our calculation. We will use XF equal to 25. And now we continue to solve the Weinberg equation. So as we said, you have the Lee-Weinberg equation written in Y, somewhere here. But we have to keep in mind that now dark matter is not relativistic. So the Y equilibrium has the Boltzmann suppression, okay? So we can simplify the equation just by considering Y, because Y equilibrium will be much smaller with respect to Y of dark matter. And so we can by writing the Y over the X equal to minus sigma V S Hx Y squared. So we can move Y on the other side. We integrate this from the freeze out to infinity. And this will be equal to y0 minus y at freeze out. This time, instead, we can neglect y freeze out, because for sure y now will be smaller with respect to y at freeze out. So the inverse means that this can be neglected. And so we can simply find that y0 is roughly equal to the inverse of the same integral from freeze out to infinity of the other side of the equation, sigma v s h x dx. Okay, from now on it's basically writing sigma v h x as a function of x, making the integration, and we can write, so we can find the y0, and then we can put y0 into the equation for finding the relic density, that is equal to the dark matter mass, entropy today, co-moving number density today, h squared, divided by rho critical. Okay, this is the general equation to find the dark matter relic density. And in y0, we find the solution of this integral. And we can write this with the most important quantities, so the dark matter mass, the freeze out, these are the numbers of degrees of freedom, and then the thermal cross-section. Then we can put for the freeze out the value of 1025 that we said before. For G star we put 80, and finally we can find that this is equal to 10 to the minus 26 centimeter cube per second as a function of sigma v. We keep the dependency with sigma v. And so basically you find that for a sigma v that is roughly the thermal cross-section, it's called thermal cross-section, so it is between does it move? Why is not changing the slide? Okay. So for a cross-section, here this is a plot of the cross-section that provides the correct relic abundance of dark matter as a function of mass. You can find that the result here, for which the relic density basically does not depend on mass, is not that incorrect. In fact, the thermal cross-section is basically flat for dark matter masses between 10 GeV up to 100 TeV. Okay, And the value is roughly basically between 2 and 2.5. So this is the correct value of the thermal cross-section that provides the right relic abundance. Okay? Here we assume the dark matter to be a Majorana particle, so particle equal to the antiparticle. But in case is a fermion, the cross-section is basically twice that number. And the reason is that in the Lee-Weinberg equation, you have to consider particle, antiparticle, and so the total density is twice the density we see here, and the cross-section is also twice to keep the same relic density, okay? So when you have a dark matter model, and when you try to fit some excess in cosmic rays, you always have to keep in mind that you should have a number for the cross-section that is not that far from this 2, 3, 10 to the minus 26. Until you include some, let's say, more complicated things like dark matter with a mass that is basically twice the mediator, so you have a resonance, or you invoke some more exotic things, okay? So for Indira detection, the good dark matter candidate is the one with the cross-section of that value, okay? Let's make 5 minutes of break. Okay, so I think there are still someone that has to go back. Okay, so what we have seen with the freeze out is that with the cross-section of the order of 2, 2.5, 10 to the minus 26, and the mass of the order of, let's say, tens of GeV up to even, I mean, the higher part of the mass is basically constrained by just the unitarity bound. But let's say with the mass of the order of 100 GeV of TV scale, you get the right relic abundance. And this is called the WIMP miracle, because with the mass that was very well tested at LEP, so the mass of electroweak gauge bosons, and with cross sections that are of the order of the electroweak ones. So at the time, basically, all the numbers were very well studied. With these two setup of cross section and mass, you fit magically the relic density. Okay. So this WIMP miracle brought physicists to devote a lot of funds to search for these WIMP interactions. Still, we have no conclusive proofs that we have detected WIMPs, even if there are some clues, as Pedro already showed yesterday, and as we will see in the next few days. But nature could have been not as nice with us as we might expect in the WIMP case, because dark matter could have been never in thermal equilibrium. And so you could have reached the right relic density with another mechanism, for example, the freeze-in. In the freeze-in case, dark matter in the early universe had an incredibly small density, and the typical couplings for dark matter annihilation was very, very small. So this means that the annihilation process, so dark matter, standard model, was working only in this direction. Okay, so the other direction was basically negligible. So if we write again the Lee-Weinberg equation, we saw before that in general, you have C production minus C annihilation. Okay, in freeze-in, this component is basically zero. So you only have C production. So you only produce dark matter particles through standard model interactions. So we can now do a very simple calculation, just to give you the rough numbers. So C production is proportional to the standard model equilibrium density for the species A and B, multiplied for the sigma V of this interaction. And the standard model particles, A and B, were relativistic, so they are proportional to the degrees of freedom of these particles, a temperature to the cube. For sigma v, we can take something simple that has 1 over energy squared, so 1 over T squared. And we include the coupling, lambda. So we have to constrain lambda. How much lambda should be to get the right relic density? The what, sorry? A and B? No, A and B are the standard model one. Okay, so the only way to produce dark matter is that the standard model particle A and B annihilate or interact and produce dark matter. Okay, we don't care about the opposite because the density initially for dark matter is incredibly small. So it was very unlikely to have this annihilation of dark matter particles. So the C production, following all these rules, it's basically Ca squared. We assume the two particles A and B to be equivalent. T to the fourth power. Then we can again solve the Boltzmann equation as we did before. And we can find that the density now of dark matter, so Y0, is basically equal to Ga to the second power, lambda squared, Planck mass, pi to the fourth power. We neglect some factors that are not important, but this is important, T final. Okay? So you have the proportionality with the coupling constant, and this is inverse proportional to T final. What is T final? T final is the temperature at which you stop the production of dark matter particles. Can you imagine what is basically the temperature? What does it mean, the temperature at which you don't have dark matter particle production? What should it be? Exactly, should be related to the energy of the standard model particles. It's more or less of the order of exactly that. But why it stops to generate dark matter particles? Mm-hmm. Ah, okay, you're talking about just the kinematics of the process, okay. But actually, we have to consider that the density of standard model particles, when they become non-relativistic, the density has the Boltzmann suppression, okay? So when standard model starts to be non-relativistic, their density start to drop significantly, okay? So the T final, that is of the order of the dark matter mass, is the temperature at which standard model particles become non-relativistic, their density drops, and so also the production is very rare, okay? So by using this and putting this in the relic density, we can find that the relic density of dark matter is basically 10 to 22 Ga to the second power, lambda squared, and then you have mass of dark matter divided by T final. T final, we can put it of the order of the mass. G is of the order of unity. It depends if the standard model particles are fermions, they are scalar or bosons. But basically, the order of magnitude is 10 to 22 lambda squared. So you can see that lambda, to work in the freezing case, should be of the order of 10 to the minus 1, 10 to the minus 11, 10 to the minus 12, okay? This is the reason why this mechanism is so unfortunate for indirect detection, okay? Because with this kind of coupling, it's basically impossible to get in an indirect detection signature. But we don't know nature what decided for us. So we have to keep in mind that this is a perfectly reasonable model to consider. Exactly. We have to do something in the early universe. Yeah. But still not for dark matter not for particle properties. It's difficult. So basically, it's almost impossible in that case to find the dark matter particle interactions. Yeah. But it was not never in thermal equilibrium dark matter because, as I said, it starts with a very very low density, and so was never in thermal equilibrium basically. Okay. Between dark matter and dark matter. Yeah, exactly. This is why a lambda of this value makes indirect detection production so small, okay? Because this lambda is typically the coupling constant we work on with indirect detection is a fraction of 1 or 10 to the minus 2, okay? Yeah. Yeah. In this case, initially, but basically also when the dark matter particle density increases, it's very rare because of the initial number density, okay? So if you plot the number density of dark matter, the number density at the beginning is extremely small. It increases due to production, and then it reaches a plateau. This plateau happens when the Boltzmann suppression of the density of standard model particles makes basically a drop in their density. So when you have the drop of the standard model, you stop the production of dark matter. Okay, so we typically we don't care about the annihilation of dark matter producing standard model. The crossover, maybe yes, you can have an effect of, but just here we are just doing a very simplified calculation. Then, if you want to calculate the freezing properly, you have to take everything into account. Yes. Okay. Other questions? Okay. So now we move to the dark matter density. That is a very important quantity for indirect detection. So one way to find so first of all, we found that the density should be basically 1 over r squared, but this was assuming no collision, an equilibrium in the density of galaxies, but this is actually not true because the Milky Way, for example, had a very important merge with another galaxy a million and million or maybe giga years ago. Recently, there is a Sagittarius dwarf that is actually colliding with the Milky Way. So this merge history of the Milky Way makes the density distribution and the velocity distribution basically not the one that we studied before, okay? And in order to find the correct density distribution and velocity distribution, you have to use numerical simulations, okay? So n-body simulations that are basically telling us that in the inner part of galaxies, the density should be proportional to 1 over r. In the outer part of the galaxy, it should be roughly 1 over r cube. Okay? So one of the most studied density profiles is the Navarro-Franken-White. So the density Navarro-Franken-White, that is rho s r r s. So this is the proportionality in the inner part of the galaxy, 1 plus are Rs to the second power. No, wait. Okay. Then what we have to do for finding basically all the parameters of the dark matter density is that we have to find rho s, that is a simple normalization, and Rs, that is a scale factor. So the scale factor basically is telling you where you have the transition between the two slopes. And this is expected to be roughly at 10, 20 kiloparsec, okay? And one way we can basically constrain these parameters is with the study of the rotational velocity. So we take the data for the rotational velocity. We have to keep in mind that in the galaxy you don't have only dark matter, you have the bulge component of stars, you have the gas component, you have dark matter, okay? And so what you can do is that you can model the velocity distribution of all these components, and you can try to fit the rotational velocity data using these three components. Then each of these components has some degrees of freedom, at least 2. So here we have a total of 6 parameters to fit. But the data are still precise enough to find that basically the local dark matter density should be between 0.3 and 0.6. And the typical scale at which you have the transition is between 10 and 20 kiloparsec. Okay. Perfect. So if we use these numbers to calculate the total dark matter mass in the halo of the Milky Way, you find that this is of the order of 10 to 12 solar masses, with a virial radius of the order of 100, 200 kiloparsec. Then you can calculate the average velocity of dark matter particles that is of the order of 200 kilometers per second. Okay, so this is the typical numbers considering a framework, a benchmark for the number of Frank-White. So here you see that why basically this motivates what I said before. So P wave dark matter, where the cross section is proportional to V squared, gives a cross section that is very, very small for our galaxy. Okay, so if you have a P wave dark matter, the contribution to indirect detection is extremely small. There are other models for dark matter density. There are in particular chord profiles like the Barkert or like the isothermal that are flat in the inner part of the galaxy. In the inner part of the galaxy, actually, you have a big uncertainty. The main reason for this is that the rotational velocity data are available basically above 1 kiloparsec. So there are no rotational data that are not very precise inside 1 kiloparsec. And so it's impossible to constrain precisely the inner part of the density profile. There you see the plot of the different profiles. Navarro, Frank-White, and Asto are called Caspi profile, and instead you have the core profile of isothermal and Barkert. When you do indirect detection, you have to take into account the uncertainties related to the dark matter density distribution. And these profiles are very different here, while instead they are basically very similar at the local distance, so around the solar system, because around the solar system we have measurements for the density that are not that different with respect to the one in the inner part of the galaxy. So the local dark matter density nowadays is basically between 0.3 and 0.4 if we take probably, let's say, 1 sigma variation. If you want to be generous and more conservative, probably you have a range between 0.2 and 0.6. And the units are GV over centimeter cube. Okay. So when we do indirect detection, typically we don't perform a fit to the rotational velocity data because we want to have something quick to evaluate. So typically what we do is that we use these two measurements. One is the local dark matter density, and the other one is the total dark matter mass for some radius smaller than the virial radius. Okay? And so if we take a density profile that is a normalization, and then you have a function of Rs and R, we can use the first, basically the first quantity to fix rho s, okay, because we do rho r equal to r local, this must be equal to rho local, and this is equal to rho s f rs r local. So we can use this relation to fix rho s, and the most difficult part is to find rho s with the mass. In particular, you know that the mass is given by the integral so we have to integrate this quantity with rho s function that is a function only of Rs divided by multiplied for the function f Rs. Okay, so this is a number that comes from observations, and all you have here is just a function of R that is integrated out and Rs. This can be solved numerically, and there you can find the values for the different density profiles for Rs and Rs found exactly with this strategy. Okay? When we study dark matter in astroparticle physics, in particular using radiation, we typically choose, let's say, three sets of astrophysical objects. One is, of course, the Milky Way. As I will show you tomorrow, the Milky Way, and the center of the Milky Way is the direction from which we expect the largest flux of gamma rays in the universe. So you have the Milky Way is a possible target. Another, and the Milky Way, the dark matter density follows those results. Or you have a Milky Way dwarf spheroidal galaxies. So these are satellite galaxies of the Milky Way that have a size of the order of 10 to 6 solar masses. And these are probably the most studied targets for indirect detection with dark matter, with gamma rays, sorry, because they are, basically they have only stars, a number that is between tens up to thousands, but not that many. And they are very poor of gas, so they don't have a lot of gas. They don't have star formation, so they don't emit cosmic rays. So basically they have zero or almost zero astrophysical background. Okay, so when you study gamma rays from a dwarf, you are basically statistically limited. You are not background limited, you are statistically limited because the background is basically zero. Okay? So the mass is basically 10 to 6 solar masses, and the size is between, let's say, tens of parsec up to hundreds of parsec. And I will show you tomorrow how we study exactly the dwarf with Fermi-Lat data. Another possible set of targets are clusters of cluster of galaxies. And there is a drawback and an advantage studying clusters. The drawback is that actually they have a lot of star formation, they have a lot of AGN activity, a lot of cosmic rays, magnetic fields, and so we expect a large astrophysical emission. So if you want to study indirect detection using cluster of galaxies, you have to know very, very well the astrophysical part. The advantage of studying galaxy clusters is that cluster of galaxies are the biggest gravitational astrophysical objects with dark matter. So they have a total mass between 10 to 14, 10 to 15 solar masses. So as the center of the galaxy, clusters of galaxies is the place where you expect the largest density in the universe. So pointing your satellite towards clusters of galaxies is something that, of course, you have to try. Okay. Okay, in the last few minutes, I just wanted to introduce you one of the simplest model we can study for indirect detection, but also at collider and direct detection. This is the singlet scalar model with an Higgs portal. So basically what we do is that we add, so I just wanted to introduce this model now because then tomorrow and in the last day we will use this model to put constraints on dark matter in the case we fix a specific model and we don't work just with the model-independent assumption. So in this model that we can label as SHP, so singlet scalar Higgs portal, we add to the standard model a scalar S, and so the part that we add to the standard model includes the kinetic term for the S scalar, and then you have a potential that is very similar to the standard model X1 with the square factor. Then you have the quadratic term. And the most important part is this portal between the standard model X and the S particle. So this is before the electroweak symmetry breaking. After the electroweak symmetry breaking, where H takes 1 over square root of 2, 0, V plus H, you have from this term something like 1 over 2, then you have the value of the X, H S squared. So this is the most important term for this model that gives a very rich phenomenology that you can see there. So basically you can have the S dark matter particle annihilates into a Higgs, then the Higgs does what we know from the standard model, produce fermions, bosons. The S can couple with this quartic term with the Higgs or produce the Higgs also with this term, or with the loop we have the production of gluons or photons. The advantage of this model is that you just have two parameters, that is the coupling between H and S and the mass of the S particle. So it's very, very simple. It's basically has the same numbers of parameter of the model-independent approach. In the model-independent approach, you have sigma v and mass, and here you have the coupling lambda and mass. The second very important advantage is that the branching ratio are all known because they comes from the standard model, because the mediator here is the Higgs boson of the standard model, And we know very precisely how the Higgs boson generates the different standard model particles. And it gives a very rich phenomenology also for collider physics, because the Higgs can decay into the standard model, into the dark matter particle. So the Higgs can go into the S dark matter particle. And so this decay contributes to the decay of the Higgs particle. And there are very precise measurements for the invisible Higgs decay. Okay? And of course, also for the detection, this can be constrained in a very powerful way. Okay, let's stop. Questions before we, yeah. Ah, true, is that true? This one, the square root? Yeah, this is V0, is the valve of the X. Yeah, sorry for my hand writing. Yeah. This is after the electroweak symmetry breaking. You have H as squared. Okay. So here you have 4, but then H takes the square of this. So when the V couples to S squared, when you have the double product of this, you have VH and S squared. Yeah. Other questions? Okay, if not, we can stop here. Remember that this afternoon we have the exercise session, and we have office hours. Okay? Okay, thank you.